Next level.
Remainders theorem is extremely important for entrance examinations. Let us start with remainders theorem.
So this is the first topic, remainders theorem, and we are going to learn from the very basic that can help us to solve even the complicated problem statements based on the remainders theorem. What we have observed over the years that there are a good number of problem statements based on the remainders theorem for all the MBA entrance examinations, whiz, CAT, GMAT, GRE, XAT, and other similar entrance examinations. In fact, this is not a new topic. We have also been taught remainders theorem during our school days, but the format was completely different. In the format in which questions are asked in the MBA entrance examination, it's completely different. So firstly, we should be able to identify the formats, two different formats. The one which has been taught in our school days and the one which we see in today's MBA entrance examination. So let me try to show you the difference between two different formats so that you can easily recall your school day learning. So during our school, I believe that this is the same way teachers used to write, that they used to draw a line like this, wherein the center area takes the value of dividend. This space takes the value of divisor, and the one at the top takes the value of quotient, and exactly at the bottom, finally, we get the remainder. But on the contrary, in today's MBA entrance examinations, the same problem statement is expressed in the ratio format. So ratio already has a numerator and denominator, but the value in the numerator is expressed as capital D, dividend, and denominator as a small d, which is divisor, for the problem statements based on the remainders theorem. So do not get confused whenever you see any number in the ratio format. If they are only asking about to find out the remainders, then express numerator as dividend and denominator as divisor. Else the problem could be from other topics, not from the remainders theorem. Also, during our school days, teachers used to give us a formula. In fact, that was also written even in all those standard textbooks, which is dividend, capital D, equals to divisor, which is a small d, into quotient plus R. I hope that you are able to recall your school day learning. And now this can also be read that when an integer d, capital D, which is already written in the numerator, gets divided by a positive integer, small d, then we get the remainder. And this remainder has to be greater than or equal to 0 and 1 less than small d, which is a divisor. So let's take an example just to understand the range of remainders. Let's take the very basic example, which is expressed in the ratio format 7 upon 2. So 2 as a divisor is deciding the remainder, and the remainder can range from 0 to 1. So for this 7 upon 2, as we already know, the remainder has to be 1 without doing any further calculation. And let's see, as we discussed just now, that the remainder has to fall in between the range of remainders. The value of remainder has to be greater than or equal to 0 and one value less than the divisor. So in this case, the set of remainders vary from 0 to 1. So a divisor value 2 can have either 0 or 1 as remainders. Again, the value of remainder will keep on changing from given a dividend, which is already expressed in the numerator. Let's say for 7 upon 2, it is only 1. And what if it is 8 upon 2? Then the remainder has to be 0. But as we can see, that remainder is either coming as 0 or 1. So irrespective of any dividend value expressed in the numerator, let's say 99 upon 2, again in that case, remainder has to be 1. So the conclusion is that the remainder has to be either 0 or 1, which is purely decided by the value given in the denominator, which is also known as divisor. So just to summarize the above learning, I am repeating the same thing again, that remainder can never be negative, but we will also practice negative remainder as a tool just to solve a complex problem statement based on the remainders theorem. But the final answer of remainder will never be a negative value. Don't worry. We are also going to practice some moderate to slightly difficult level problems wherein we can easily be identifying the use of negative remainder only as a tool but not as a final answer. Now there's another variation of remainders theorem that can also be expressed as polynomial. This is completely a new format wherein there is no number expressed in ratio. In fact, there's a function even in the numerator as well as in the denominator. If a polynomial function is divided by, let's say, x minus a being the constant, then how to find out the remainder? So let's see how we do that. We simply take the function written in the denominator, and here in this particular example the function is x minus 2. So simply equate this x minus 2 with 0 and the value of x becomes 2, and now put this value in the polynomial function which is expressed written in the numerator. So after putting the value of 2 in the numerator, x cube becomes 8 and 2x square again becomes 8. Minus sign is already over here. Plus 6. 3 into 2 becomes 6 minus 4. And the final value comes over here is 2. Then this 2 is the remainder for this problem statement. So this is another variation which you can also find in any mock paper or in any standard textbook. So just to give a very basic idea for all those aspirants who come from non-mathematics background, so these functions are known as polynomial function, usually written as px, and there are different definitions based on the number of terms and based on the number of degrees. So based on the number of terms, polynomial functions are known as monomial, binomial, trinomial and polynomial, and based on degrees it is further categorized as linear polynomial, quadratic polynomial, cubic polynomial and so on. But again, this is not our discussion. We are only supposed to find out the remainders even for polynomial functions, even if it is expressed in the ratio format. Now let's come to the second learning, which is very important. In fact, the most important thing. We are again coming back to the problem statement wherein numbers are there in numerator and denominator, but the numbers in the numerator are expressed with positive sign and multiplication sign. So there are different numbers in the numerator but has mathematical sign of positive and multiplication, and also combination of positive sign and multiplication sign in the numerator for all such numbers. So just to make it simpler, let me try to explain this new learning. Let's say point number 2. The first one is a remainder of a sum where all the numbers written in the numerator are only expressed with positive sign. For example, let's take 4 plus 6 plus 8 plus 12 upon 3. So these numbers are only expressed with positive sign in the numerator. Now let's try to apply the core understanding of remainders theorem. So for all these values which are already separated by a positive sign, then we have to tackle each number separately. That's the only objective. So for the value of 4, when divided by 3, it will yield 1 as the remainder. So simply write 1 exactly above the value 4. And just for our understanding, as a rough work, let's put a red mark for this individual remainder. This is the most important part of remainder theorem. We'll do the same exercise for 6, 8 and 12 individually. So for 6, it yields 0, and again we are putting a red mark for this value 0, and for 8 it's 2 with a red sign, and with 12 it is again 0. Now in the very next step, what we are supposed to do, we are simply going to replace the already existing numerator values with all these new red mark values. So now in the very second step, we are removing 4, 6, 8 and 12, and instead of that we are writing 1, 0, 2 and 0 with all these signs as it was written earlier in the very first step. So here we have got only positive sign, and for that reason I'm only placing positive sign in between all these new values. Now let's simply add these two, and it gives the value 3, and obviously 3 upon 3 will yield remainder as 0. So we can see that this is the shortest strategic technique and very useful for remainders theorem problem statement. In relation to the above, when a numerator is completely divisible by denominator, then the denominator being a divisor is also known as factor. And even in any problem statement, whenever you find the word completely divisible for any ratio, then you should also come to a conclusion that the numerator will be completely divided by the denominator, and it will yield remainder as 0. So this is a very subtle point, but no worries, as we see different problem statements, we'll keep on exploring the core concepts into solving real problem statements. Let's say this is point number 2c, remainder of a power, and for that reason, and just to understand that, let's take a very basic example, 4 to the power 6 upon 3. So we have got 3 different problem statements. The first one, which is expressed with positive sign, the second one is purely expressed with multiplication sign, and the third one doesn't have any sign, but the value, the base value 4 has got a power. One more thing which is relevant to our discussion, that what happens if the power is a large number. Can we really solve such problem statement when power is really a large number by simple techniques, by simple core method? Yes, we can. And also there are 2 different techniques that can also be that can also use to solve to find out the remainders for a given ratio. When in the numerator the base number has got a huge power, and these 2 new techniques, by the way, it is just a technique, not any formula, are known as first, cyclicity of remainders, and the second one is based on Euler's theorem. Let's say there's a ratio which is 2 to the power 100 upon 7. Now, as we can see that 100 being a huge number raised to the base value 2 in the numerator. Okay, first let's try to focus on the cyclicity of remainder. Again, for the same problem statement, 2 to the power 100 upon 7. Let's say if the power were 2 to the power 1. If the power were only 1 raised to 2 upon 7, then it yields remainder as 2. But if the power is 2 raised to the base value of 2 upon 7, then obviously it becomes 4 upon 7 and the remainder will be 4. Now following the same pattern, if it is 2 to the power 3 upon 7, then it becomes 8 upon 7 and the remainder becomes 1. And 2 to the power 4 upon 7, which is 16 upon 7, will yield remainder as 2. And also for 2 raised to the power 5, which is 32 upon 7, results 4 as the remainder. Now can we observe a pattern? The remainders are following a pattern of 2, 4 and 1. So the remainder for the problem statement 2 to the power 100 upon 7 should have a remainder either 2, 4 or 1. So such techniques is known as following a cyclicity to find out a specific remainder. No worries, in today's small lecture we'll see a problem statement which can be solved by using the cyclicity of remainders, and that problem statement can also be solved by using the simple core concept based on remainders theorem. So as of now, I only want you to introduce the cyclicity of remainders. Now can it really be solved by using simple core concept which we discussed earlier? Because it sounds like even 2 to the power 100 can also be written as 2 into 2 into 2 up to 100 number of times, and it follows the point number 2b, wherein the numbers in the numerator are expressed with multiplication sign. Now as we have already seen earlier, even for this problem statement, if we are not able to apply cyclicity of remainders, then there is an alternative way to solve the same problem statement, 2 raised to the power 100 upon 7. So this numerator can also be expressed as 2 cube within a bracket raised to the power 33 into 2 upon 7. So the reason that I chose 2 cube inside this bracket, which is also 8, because this 8 is very close to the value 7. So we have to express our numerator in such a way that the resultant value is very close to the multiple of divisor. And if it happens so, and if it is expressed in such a way, then solving and to finding out the remainder really becomes very easy. Now applying the same thing, the same concept discussed earlier for this 2 cube, which is 8, can be written for 33 times in the numerator, and yes, there's an extra 2 that is completely a separate thing. So now for every 2 cube, the remainder individually is coming as 1, and because there's a multiplication sign in between, then for this entire value 8 being repeated for 33 times, every number has got a remainder 1, and obviously 1 multiplied with 1 for n number of times will always yield 1. So finally, because there was an extra 2, and because of this 2, the resultant value is coming as 2, and 2 upon 7 will yield the final remainder as 2. So we have just seen that by applying the core concept, we can also solve even the complicated problem statements based on the remainders theorem if we are not able to identify any cyclicity or any pattern, etc. Now, coming to the second technique, which is Euler's theorem. Though Euler's theorem has got some limitation, and Euler's theorem is only applicable for such remainders problem statement wherein there is a huge power raised to the base value given in the numerator. Now for example, let's take another value, which is 3 raised to the power 100 upon 7. Now Euler's theorem states that if the base value, which is 3, and the number given in the denominator, which is 7 over here, are co-prime numbers. So co-prime numbers are a set of numbers whose highest common factor is always 1. So 3 and 7 has a SCF as 1. So further, simply subtract 1 from the value given in the denominator as the next step. So in our case, 7 minus 1 is coming as 6. So as per the Euler's theorem, and because of this value 6, if this value 6 is coming as a power to the base value, which is 3 over here, and then 3 raised to the power 6 upon 7 will always yield 1 as the remainder. But in the problem statement, it is 3 raised to the power 100 upon 7. So we can also express 3 raised to the power 100 upon 7 as 3 raised to the power 6 within a bracket and 16 over here, and follow the same core concept to find out the remainders.
3, 2, 1.
Now let's jump to the next learning. Using of negative remainder as a tool. This is the most important part of remainder's theorem. Now let me try to explain it through an example without giving any further lecture. Let's say there's a ratio 41 upon 4. So usually till now we have only seen and discussed positive remainders. So 41 upon 4 will yield 1 as the remainder, a positive remainder. But what about negative remainders? Yes, I repeat the same thing, that negative remainders do not exist in reality, but we can use a negative remainder just as a tool. So whenever we see negative remainders anywhere, then we are only using as a tool, and that is not the final answer. If we are getting negative remainder in the very last step, then we are supposed to convert the negative remainder to the corresponding positive remainder, and that positive remainder becomes the final correct answer. So I'll try to explain the logic in between the positive remainder and the negative remainder, but I have also got from the examination perspective a very basic formula that anyone can easily memorize, which is a positive remainder. A difference between a positive remainder and negative remainder is always equal to divisor. Let's say there is a problem statement which is 43 to the power 40 upon 4. So as we have seen earlier, which is 43 can be expressed as 43 into 43 into into 43 up to 40 number of times upon 4, and for every 43 identify 40 as the multiple, then positive 3 is the remainder for every single 43. Now all these positive 3 which appears in the next step is also huge number. I mean will again be clubbing positive 3 with another value so that it becomes 9, and if it is 9, then 9 can be expressed for 20 times, and for every 9 there's a remainder 1. Finally we see that the ultimate remainder is coming as 1. Let's again go back to the very starting. This problem came from when the value was positive 3, and for that reason when we identified our multiple for 4 as 40, but what if we identify the multiple of 4 as 44 rather than taking 40 as the multiple? Now let's take an alternate way wherein we can simply apply negative remainder as a tool, only as a tool. So let's say the distance, if every 43 is expressed for a 40 number of times, then every single 43 will yield minus 1 as the remainder. That's the leftward distance from the 44, and if it is only minus 1 coming individually, then there's no need to multiply on the paper. This minus 1 getting repeated for 40 number of times, even number of times, will obviously result a positive 1, and 1 upon 4 will yield 1 as a final remainder. So this is the learning that we have seen, where to apply positive remainder as a tool and when to apply. Now let's learn some very common problem statement based on the remainder theorem. Let's say if there is a very huge number which doesn't have any power written in the numerator. Let's say if this number is 4, 5, 2, 6, 9, 8, 5 upon 10, then the unit digit place itself becomes a remainder of 4, 5, 2, 6, 9, 8, 5, which is 5 over here. Now if the same number 4, 5, 2, 6, 9, 8, 5 is getting divided by 100, then the last 2 digits of the numerator becomes the final remainder, which is 85 over here. Now let's take another problem statement which is relatively more complicated. Let's take another example as 44 raised to the power 43 upon 10. Now the number in the numerator is a very huge value, which can also be expressed as 44 into 44 up to 43 number of times. And yes, that can be solved even by using the core fundamental learning of remainders theorem, which we have already discussed. But now let's see a smart way for such problem statement. What we can do, let's try to express the given value in the power in the form of 4k. So this 43 can also be represented as 4k plus 3. We are not that concerned with the value k. K could be any positive number. We are rather more concerned with this value 3. So this shortcut technique seems to focus on this given value 3 and the unit place number of this base value, and to avoid rest of the numbers because it is already in the power format. So we can reread the same thing as 4 to the power 3, avoiding rest of the numbers. And 4 raised to the power 3 gives 64. So just take the last the unit digit of 64, which is 4 over here. And so what I'm trying to say, that 44 raised to the power 43, if it is expanded, then there will be only one resultant value, and the unit place of the resultant value will be 4. And as it is already mentioned in the problem statement, that the entire numerator value is divided by 10. And as we have just seen that if the numerator is divided by 10, then the unit digit place of the numerator becomes a remainder, ultimate remainder. So for this huge number 44 raised to the power 43 upon 10, without solving, we can say that 4 is coming as the final remainder. Now let's try to apply a similar type of problem statement wherein there's a slight difference. Now for the second problem statement, which is 44 raised to the power 43, but this time in the denominator it is not 10, it is rather 100. So we'll apply the same learning which we have just seen, but now this time we are not only focusing on the unit digit place of that big huge numerator value, we rather focus on last 2 digits of that big numerator value, and it is only because of these 2 zeros written in the denominator. So as the number of zeros increases in the denominator, we keep on increasing, we keep on focusing on the digits from the last in the numerator. So let's apply the same learning in this problem statement. So first, let me express this 43 in the form of 4k. Always remember to express only in the form of 4k. I mean, it can also be expressed in other values also, but for our understanding, let's only try to express in the form of 4k. So this 43 is again coming as 4k plus 3, but this time rather than focusing only on the last unit digit place of this entire 44, let's focus on both the values. That's the only difference, and the resultant value will have 44 raised to the power 3 as the last values. So let's do one calculator. This 44 into 44 into 44 is resulting as 848184. So we are only considering 84, the last 2 values of this big huge number, and this 84 becomes my final remainder.
I think we should practice questions based on the learning so far. Try not to use calculator now.
Now let's take a real problem statement from CAT paper asked in the year 2024. When 3 raised to the power 333 is divided by 11, the remainder is. Okay, so from this for this problem statement, as we have discussed just now, can we really apply the Euler's theorem in this problem statement? Yes we can, because 3, the base value, and this 11, it has got an SCF of 1, and for that reason, as per the Euler's theorem, 1 has to be subtracted from this base, from this denominator value 11. So this 11 minus 1 results to 10. So it means that 3 raised to the power 10 upon 11 will always have 1 as a remainder, and this 3 raised to the power 333 can be expressed as 3 raised to the power 10 within a bracket 33 over here into the remaining 3's, which is 3 raised to the power 3 finally upon 11. So for this starting 3 raised to the power 10, it will always yield 1 as a remainder, and for this remaining value, which is 3 raised to the power 3, which is 27, that 27 upon 11, and finally the value is coming as 5. Now what happens if we are not able to recall any theorem or any formula per se on the examination day? So can we really solve it by using core technique? Yes, we can always. Can we really rewrite our numerator and express in a way that the value in the numerator is coming very close to the multiple of denominator, and we can mentally find that multiple of 11. So that's the beauty, because we have to do it mentally. If we are using pen and paper for finding out the multiples, then it doesn't serve the purpose. So as we all know, for 11 we can also take 11 as a multiple itself, or 22. And if we are expressing 3 raised to the power 333, then in my opinion, let's take 11 as a multiple of 11 itself. And the reason is that we can express 3 raised to the power 333 as 3 raised to the power 2 within a bracket, and 165 over here, and the remaining 3's over here, which is 3 raised to the power 3. So for every 3 square, which is 9, having 11 considered as the multiple, so the distance is coming as -2. So here it is convenient for us to use negative remainder as a tool, rather than taking a positive remainder. So every -2 in the next step will replace the entire value in the numerator, and finally it is coming as -2 raised to the power 165 into 3 to the power 3 upon 11. Now let's take it to another step, that is -2 raised to the power 4 within a bracket, then 41 over here, then -2 3 cube upon 11. Further it becomes 16 raised to the power of 41 into -2 into 3 cube upon 11. Finally, the 16 yields 5 as the remainder. As we have already considered 11 as the multiple, now this 5 raised to the power of 41 into -2 into 5 upon 11. We can simply increase this power of 41 to 42 by removing this one extra 5. Now this 5 raised to the power of 42 can also be written as 5 cube within a bracket to the power of 14 into this -2 upon 11. Five cube is 125, which also yields 4 as the remainder. Then it becomes 4 raised to the power of 14 into -2 upon 11. It can also be written as 16 to the power 7, and 116 yields 5 as the remainder. So this is 5 raised to the power 7 into -2 upon 11. And further, there are two 5 cubes. And one extra 5 into -2 upon 11. So every 5 cube yields 4 as the positive remainder. Finally, it is 4 square into 5 into -2 upon 11. And finally, as a result, we get -6 as the remainder. But we also know the very fact that there cannot be any negative remainder. So we are now supposed to convert this negative remainder to the positive remainder. And by using the same formula which we discussed earlier, and by putting the values over here, positive remainder is coming as 11 minus 6, which is 5. So finally we have got a positive remainder as 5. Now there's a learning. Let's say if we forget even this basic formula, which is the difference of positive remainder and negative remainder is to divisor, we can also represent the same thing on a number line. And in this case, because 11 was the identified multiple and it can only have a range of remainders from 0 to 10. So in the red color, I have written all these positive remainders, and for every positive remainder, there is a corresponding negative remainder which is highlighted in blue color. So even on a number line, we can see the correlation between positive remainder and a negative remainder. And I believe that just by some basic practice, all these mental conversion of positive remainder to negative remainder and vice versa can easily be done, even if we are not able to recall that very basic formula, which is the difference of a positive remainder and a negative remainder is equal to the divisor. Now let's take another problem statement which states 29 to the power 29, again the power 29, and the entire number is divided by 9. And this question is asked in IPMAT 2019. So now there is no need to use any formula. It can easily be solved by using cyclicity of remainders. But the only challenge is that it has got two successive powers. Earlier we have already seen that there was only one power to the base value, but in this problem statement it has two powers. No problem at all. We'll do the same thing again. So for the time being, let's apply the cyclicity of remainders. But firstly, try to reduce this base value 29 to the smallest possible number as per the remainders theorem. Now, just by observing the pattern, we can easily say that the base value 29 is being repeated for n number of times. But this n number of times is not known to me as it has a huge power. But this 29 will definitely have 2 as a remainder for one single 29. And for all the remaining 29s, it will definitely be having 2 as the remainder. So it means that we can start from the very first value, which is 2 raised to the power 1 divided by 9, not 29 raised to the power 1 divided by 9. And then it yields remainder as 2. Following the same pattern, 2 raised to the power 2, which is 4 divided by 9, and it leads to remainder 4. Further, 2 raised to the power 3 divided by 9 yields the remainder as 8. Then 2 to the power 4 divided by 9. Remainder is coming as 7. No, there is no repetition as of now. Then 2 to the power of 5 upon 9. Remainder is coming as 5. So we have got 2, 4, 8, 7, 5 as remainder. Okay, now let's go further. 2 to the power of 6 divided by 9. Again, coming remainder as 1. No repetition till now. Let's go for another value. 2 raised to the power of 7 upon 9. Now this is resulting remainder as 2. But just to be 100% sure, let's take another value, which is 2 raised to the power of 8 upon 9. And yes, the value 2 to the power 8 is 256 upon 9. Okay, so remainder is again coming as 4. So now there's a clear cut repetition, and the repetition, the cyclicity of remainders follow a range of values, which is 2, 4, 8, 7, 5 and 1. Then it has a repetition, so we can easily see that exactly after 6 attempts, remainders, that we are getting the same remainders. So we have to remember the number of attempts that matters the most, and for that reason, to find the remainder of the original problem statement, which is 29 raised to the power 29, again raised to the power 29 divided by 9. Now, following the above logic, this first value 29, which is a value of power, let's say power 1, can also be expressed as 5 raised to the power 29. And once we identify that 5 raised to the power 29 divided by the length of the above cycle, which is 6, and checking it through the cyclicity of remainders, then we can say that 5 raised to the power 1 upon 6 will lead remainder as 5. 5 squared upon 6 will lead a remainder as 1. And 5 raised to the power 3 upon 6 will lead remainder as 5. And just to be 100% sure, let's do another check. 5 raised to the power 4 divided by 6, it again leads to a remainder as 1. Okay, it is by mistake that I have written 5 cube 2 times, so kindly ignore the second one. It is 5 to the power 4 only. Okay, coming back to the discussion. So we can easily observe that the set of remainders from these repeated exercise is coming as either 5 or 1. So we clearly understand that the remainder of 29 raised to the power 29 upon 6 will have the remainder either as 1 or 5. But by observing this cyclical pattern, 1 as a remainder is only coming for those values wherein the power is an even number. For an example, 5 squared upon 6 leads to 1 as a remainder. 5 raised to the power 4 upon 6 leads to 1 as a remainder. And for odd values like 5 raised to the power 1 and 5 raised to the power 3 divided by 6 is always leading remainder as 5. And here in this 29 raised to the power 29, the power value 29 being an odd number will definitely be having the remainder as 5. So just by observing the odd and even pattern, we can definitely say that 29 raised to the power 29 divided by 6 leaves the remainder as 5. But coming to the main problem statement, wherein it is 2 raised to the power 29, again raised to the power 29, and the entire number is divided by 9. So it can also be written as 2 replacing these two 29 numbers with 6k plus 5, and the whole thing is divided by 9. Okay, now for this 6k plus 5, how exactly we arrived here? 5 is the remainder, and and this length of the cycle is 6. So we can say that this 29 to the power 29 can also be expressed in the form of 6, and for 6k, and for that reason it is 6k plus 5, 6 being the divisor, k is some unknown big number which is the quotient, and 5 being the remainder. So this 29 raised to the power 29 can easily be expressed by 6k plus 5. Now finally, this 2 to the power 29, again a power 29 divided by 9, can be written as 2 raised to the power 6k plus 5 upon 9. So just randomly put any value of k, let's say 1 or k equal to 2. If we consider k as 1, then 2 to the power 6 is 64, and if we take k as 2, then it becomes 2 to the power 12, which is 4096. So this 2 to the power 6, which is 64, individually results 1 as the remainder, and that you can also check it later on, that 2 to the power 12, if it is if k is 2, which is coming as 4096, will also result remainder as 1. So this part is gone. And for this 2 to the power 5, which is 32, so this will also result remainder for this particular part as 5. So 5 into 1 will result the final remainder as 5. Now we can easily compare that by using this alternative method, which is cyclicity of remainders. Even there are multiple powers, a power raised to another power can also be solved in two different phases. That's the only difference, wherein first we dealt with keeping the base value under consideration, and secondly we focused on only the powers, and by combining these two different phases we have come to the main remainder, which is coming as 5 over here. Now this is another problem statement, and it is from CAT 2022. It is purely a word-based problem, and it says that the school has less than 5,000 students, and if the students are divided equally into teams of either 9, 10, 12 or 25 each, and exactly 4 are left out. Okay, so for all these word related problems, this is my hint and my observation that we should try to decode each and every line as much as possible. And if we are able to draw some random photos from the lines separately, then it is really very useful to proceed in the right direction without wasting time. So just by observing only the first line, I can say that there is a number, any random number, let's say n, which is less than 5,000. But whenever it is divided by 9, 10, 12 and 25, then it always leaves remainder as 4. So can we not write the very first line as 9k1 plus 4 equal to n, and then 10k2 plus 4 equals to n, and 12k3 plus 4 equals to n, and finally 25k4 plus 4 equals to n. So this k1, k2, k3, k4 are just different variables, and it all represents different quotient. But again, as I said earlier, we are not going to focus on quotients. Our main concern is to focus on remainders. And now moving to the second line, as it is already given in the problem statement, that if it is divided into teams of 11 each, then there is no remainder, no one is left out. So we can also say that 11k5 plus 0 is equal to 9.
Sorry, n but not 9.
So now we have got 5 different equations representing the same n in 5 different ways. And as per the problem statement, the examiner wants to know that if that n is divided in teams of 12 members each, then how many such teams can be formed? So we can also say that this 12k6 must be having some remainder, let's say x, and we are not aware of this x. I mean, x can also be 0, 1, 2, 3, 4, any such numbers. that we are not aware of. So for the time being, let's say that the remainder is coming as x, but the LHS should be equal to n. We can also say that this 9, 10, 12, 25, the LCM of all these values 9, 10, 12, 25, which is 900, will also have 4 as the remainder for this given number 9. So this 900 and k, let's say this k is some another quotient, the 900 and k plus 4 is also equal to 9. And if we want to check additionally, then let's take a rough number. Let's say there's a number 50, and this number 50 is equally divided by 2, 5 and 10, having the same remainder 0. And if we take the LCM of 2, 5 and 10, which is 10 itself, then 10 also has 0 as a remainder. So the LCM of these three values is also having the same remainder. And by using the same logic, the LCM of 9, 10, 12 and 25, which is 900, will also have 4 as the remainder. So finally, replacing all those different set of numbers, which is 9, 10, 12 and 25, we have come to only one single equation, which is 900k plus 4 equals to
n.
Now combining this new equation with the second line equation, which is 11k5 equals to
n.
There is no remainder as such. So we can say that n, now represented as 900k plus 4 when divided by 11, leads to 0 as the remainder. And if we do so, and if we express the same thing in this ratio format, then we can say that 900k plus 4 divided by 11 leads to 0 as a remainder. So I mean, we already know the remainder, and if we know the remainder, then we can find out this value. And let's say if we take k as 1, then it becomes 9001. And 904 divided by 11 doesn't have 0 as the remainder. And if we take k as 2, then it becomes 1804. And 1804 is completely divisible by 11. So it means that k has to be 2. And the number also has to be 1804. Now this number is obviously less than 5000, and the number identified is 1804. So finally, just express this 1804 in the form of 12. 12 and we have already taken one equation, which was 12k6 plus x equals to n. Okay, so that's the same equation which can help us to identify the value of k6. So now the k6 becomes my maximum number of teams, and for that reason, and obviously a team has to be a positive integral value. A team cannot be a decimal value or in a fraction. So just expressing 1804. So this 1804 can be written as 12 into 150, which is 1800, and then plus 4. So this 150 becomes the maximum number of teams for the student count as 1804.
To know more updates, stay tuned.
Kindly do like, share and subscribe.